So last time we talked about the basic algebraic operation for limit of sequences. We talked about the monotone convergence theorem. So the monotone convergence theorem was that you had a sequence that was increasing, or it could be decreasing. So either it was increasing. This meant that the next element was bigger or equal to the previous, and then they were all assumed to be bounded. If you had such a sequence, or similarly, if you had a sequence, so this was the increasing case, then there was a similar decreasing case where the previous is bigger or equal to the next one. And then they are assumed to be bounded from below. So this was decreasing. So monotone convergence theorem was that if you had a bounded increasing sequence or a bounded decreasing sequence, in either case, the sequence is convergent, and it's converging in the first case, in this case here, A. It converts to the sub of the xn, to the in case A. And in the case B, it converts to the inf. In case B. So that was the monotone convergence theorem. And the third thing we talk about, and that's where we will continue today, is Cauchy sequence. So we talked about Cauchy sequence. So let me, and we put a few things about Cauchy sequence, but we want to examine that more today. So let me remind you what a Cauchy sequence is. So a sequence xn is said to be a Cauchy sequence if for all epsilon greater than 0, there exists n such that if little n is bigger or equal to the capital N, then, if little n and little m, so if n and m and n are bigger or equal, then they are epsilon close together, xn and xm, the distance between them is epsilon. So this was a Cauchy sequence, and it just meant, Cauchy sequence just meant that the tail, right, of the sequence runs together. Right. Now, let me just prove. I think we maybe talk about this, but I'm going to let me just use a little theorem here. If xn is a Cauchy sequence, then xn is bounded. And so the proof of this is the proof. So now in the definition of it being a Cauchy sequence, you can take epsilon to be equal to 1. So if you take epsilon to be equal to 1, in the definition of being a Cauchy sequence, so this means that there exists some n such that if little n and little m are bigger than this n, then the difference between these two is less than 1. Right? This is the definition where I just apply it to epsilon equal to 1. Right? So you have this. But of course, in particular, we can set, say, m equal to this. Right? And then you have that xn, all the other ones. This means that for all, then for all little n bigger than capital N, if you're looking at this difference here, then this is less than 1. I'm only applying this now. I'm just choosing just one single m, and I'm choosing it to be equal to that capital. So you have that. And so this means that now you see that if you take if you take x, so now suppose that little n, so for little n bigger than capital N, if you look at such a little n, then you have so for little n bigger or equal to capital N, then you have that the norm of little n, well, you can write little n as the difference. You can write little n, right? You can subtract it first and then add it again. So this is clearly the same. And now you can just, so you have the sum of two things. You can think about this thing here as one number, and this is another number. So this is now less than xn minus x capital N plus the norm of x capital N. And this here was, because little n was bigger than capital N, this here is bounded by 1. So this is less than 1 plus the norm. This. So you see that for all the little n's that are bigger than capital N, all of those, there is a uniform bound, right? And so this means that if you're now just taking the maximum of the norm of x1, the norm of x2, up to the norm of xn xn minus 1, and then x capital N plus 1. If you take the maximum of this and call this n, then clearly for all n, clearly you have for all n, you have that xn is less or equal to n. Right? Because if little n is bigger than capital N, then it's bounded by capital M because it's a maximum in particular of this, and all the other ones, that's sort of obvious. Okay, so it means that if you have a Cauchy sequence, it's automatically bounded. Okay. Now we have the Cauchy convergence theorem. So next we will discuss is the Cauchy convergence theorem. So this is the following: that any Cauchy sequence is convergent. Okay. So remember that last time we proved the following theorem. So recall that last time we showed the converse. So namely, we proved the following theorem. We proved that if that any convergent sequence is a Cauchy sequence. And so the Cauchy convergence theorem is a converse to this. Now, so we'll come back to the proof in just a little bit. But before that, let me talk about some applications. And so the first one, we sort of started talking a little bit last time, and this is the contracting mapping theorem. So contracting, and that in itself have a number of applications. So contracting mapping theorem. And for that, I need to recall some definitions. So a map T from R into R is said to be a contracting map if there exists some constant C positive, C is positive, and the key point is it will have to be positive. So but the key point is that this constant has to be strictly less than 1. And then contracting mapping just means that if you're looking at the difference between the images, then they are closer together. They're strictly closer together than the points that they are images of. Okay, so this is a contracting mapping. Right, and so the contracting mapping, again, this here inequality is, it's saying that under the map, the images are squeezed more together. So now, that's one concept. The other one we need is that for fixed point. So the other concept is fixed point. So X here is a fixed point for a map T if under the map the points remain unchanged. So T of X is equal to X. So this is what it means to be a fixed point. Yeah.
So for that, it's not the same C for all X and Y.
It is the same C.
It is.
Yeah, it's the same C. Yeah. And we'll come back to this in just a second. But it is supposed to be the same C. You can weaken that a little bit, but essentially, I mean, you sort of, at least, we'll talk about this in just a second. But it's important. Just think about it, that it's a requirement that it's the same C for all. And the key point is that this C is strictly less than 1. Okay, so this is a fixed point. Okay. And now, so now the first little lemma is that. So we have a lemma here. If T here is a contracting map, then then there's at most one fixed point. There cannot be more than one fixed point. Okay? So let's prove that. It's proved. So I'm going to suppose x and y are fixed points. And I want to show that x is equal to y. Right? So I'm looking at the images. So let's continue. So I'm looking at the images under F. So I'm looking at, so I take t of x, and I'm looking at the difference between t of x and t of y. And I want to estimate that difference. Well, on one hand, x is supposed to be a fixed point. So t of x is the same as x. And likewise for y. So this here is the same. So t of x is the same as x. T of y is supposed to be the same as y. So I have this. On the other hand, it's a contracting map. So this here is less or equal to c times the norm of x minus y. Right? But now c here, remember c is strictly less than 1. So you can only have an inequality like this, right, if this number here is 0, right, when c is strictly less than 1. So this here implies that x minus y, the distance is 0, and so of course this means that x is equal to y. Okay, so that's what we want to prove. Yeah.
The definition of the contracting map
Yeah.
is also less than or equal to.
Yeah, I'm sorry. That was, yeah, it should have been less equal to. Because otherwise, you know, it wouldn't be, if x is equal to y, it wouldn't be that. So it should be less equal to. Okay, so a contracting map have at most one fixed point. Okay, now let's so let me just, so you're going to do this. So I have harassed the graders to give you back the homework. It should be back today. I mean, otherwise they're in trouble. So hopefully, and the assignment for next week is already posted. And here's so this is on the next. So I will. So here's something on PZ3, and I think it's okay. Yeah, I forget which one it is, but anyway, on the third PZ, you will be asked to prove the following: that if T here is a contracting map, and x here is any point in the domain of this map, then if you form the sequence an, so a1, say, that's just x, a2, let's call it a, sorry, let's call it a0 is x, a1 here is t of x, t of a0, so this is t of x, and a2 is t of a1, So this is the same as t of this, so this is t times t of x, which I will write like this. And A3, so we continue this way, A3 is t of A2, so that is t applied 3 times, so t of x, and I'm going to write this as t cube of x, and so on. So an is going to be t of it's t an plus 1 is going to be t of an. So that's the same as t to the power n plus 1 of x. Okay. So if you have a contracting map and you just start with any point you want, and now you form a sequence that is based on that point, and the nth element is just where you have applied the map n times to the original point. So if you form that sequence, then you will prove, you will show that in the homework, you will show that this sequence, so PZ3, and I will just do a special case of it that you will start with, but we'll just do this now. And then the rest, I leave for the homework. But on PZ3, you prove that this AN is a Cauchy sequence. And what is the key starting point? So key starting point for this. So now, as you hear, you're already well started on PZ3. Because the key starting point for this is to prove that it's a Cauchy sequence. So I want to estimate. So this is not enough, right? I mean, I need to prove. What I need to show is, right, remember, I need to prove that when little m and little m n are sufficiently large, then I want to estimate the distance between these two and show that they're bunched together, right? That's what we need to prove it's Cauchy sequence. I won't quite do this, but I'll do a special case that is the key starting point. And that is the way I'm looking at this thing here. I'm looking at 2 consecutive elements in the sequence, and I'm estimating the distance. Right? That's not enough to prove that it's a Cauchy sequence, right? Because I need to prove that for all n and m sufficiently large. And I'm just proving here that for any n sufficiently large, if I'm looking at the neighbor, then the distance is very small. But you can use the estimates that we will now prove to prove that it is, in fact, a Cauchy sequence. So in order to estimate this, right, I can think about this thing here as t as a to the n plus 1. This here is just t of a to the n, and an itself, this is t of the previous element, right? This is how we define them. So this means that this thing here, so again, I can just write this in here. So this thing is equal to an minus t of an minus 1. And now I can use that as a contracting map, right? Because now I have these 2 t's here. So I can use that as a contracting map, so I get less or equal to, and then an minus 1. And so you see that the distance between the next pair is, because c is strictly less than 1, it has decreased with some factor, right? And so now the key starting point is that if you just iterate this, So now if I iterate this, so I'm looking at an plus 1 minus an. And I now have that this thing here is less than c an minus 1. But now I'm writing, forget about the c for a second. I'm just writing this thing here, so I do the same thing again. I write this here as the image of an minus 1. And I write this n minus 1 as the image of the previous one. So n minus 2, right? And now, so I write this, so c here, I just have to carry along for the right. And then I have t an minus 1 minus t an minus 2. And now forget about this, just use as contracting mapping. So then this is less than equal to, and then the c I have to carry along. But then there's another c that pops out, right? So this times c that pops out because of the contracting mapping, and then an minus 1 minus an minus 2. And so you see that you have written this as c squared an minus 2 minus 1 minus an minus 2. And so now you continue it. And so you see that the further out you get, right, so you continue this all the way down to that you're getting that this element is the initial point, and this one is the first element, A1. This is A0, and this is A1, right? And so you see that you're getting something which is like a c to some power n times the distance that you started with, right? So this is bounded by something like c to the n times a to 1 minus a0, something like that. And so that's a key starting point. So if you're going very, very far out, remember that this number is smaller than 1. So this here will become incredibly small when n is large, right? And so this is the key starting point to prove that if you take a contracting map, you start with any point, and you form this sequence here, then it's a Cauchy sequence. So now, and I leave the rest for the homework. Now let's prove the contracting mapping theorem using the Cauchy convergence theorem. So using the Cauchy convergence theorem, will now prove the contracting mapping theorem. Okay, so what is the contracting mapping theorem? The contracting mapping theorem is that if T here is a contracting map, so T from R to R, maps R into R, is a contracting map. Then T has a fixed point. We already know that such a fixed point is unique. Right? We already proved that it can at most be one fixed point. Okay, so let's try to prove that. So we're going to use this result from PCH3.